So you may notice I have an accent. I'm from New Zealand originally. I've lived in the US for 9 years now, but I'm still very conscious of my accent, so I'll try and talk slowly. Please let me know if I'm talking too fast. So a little bit about Trimble and how we represent in agriculture. We've been in agriculture for many years, where we really started off in precision guidance applications, where we were putting light bars onto tractors or combine harvesters or sprayers to ensure that they can run in a straight line to avoid overlap for any application. Then we progressed that into automated steering, where we actually took control of the steering of the machine, and we can actually keep the machine perfectly aligned to sub-inch accuracy. And then we progressed into precision agriculture, where we progressed into flow and application controls, where we could actually shut off a row unit on a planter, or we could shut off a nozzle on a sprayer to ensure that when overlaps did occur, we could shut off in the right place to ultimately to decrease input costs in applications, and at the end of the day, increase production for a grower. And then, of course, most recently, we've taken that a step further, and we're starting to look more around data communications between the field and the office, and data analytics, big data, cloud-based computing, some of these buzzwords that we're hearing a lot of, but in reality, a lot of this is really the future of precision agriculture. So most recently, we've taken a much deeper look into water management and irrigation management, and I think this parallels a lot with what Fred just talked about, some of the bigger problems in the world and some of the drivers for utilizing technology in water management for agriculture. Food security, Fred spoke about the forecast for global population increase to 9 billion people by 2050. Very true, and I appreciate, there's a lot of good comments you had there around changing food supply from distribution and storage and that type of stuff, but we also live in an age of advancing technology, where we can utilize technology as one of the key elements to helping feed the world and improve food availability for the masses. Farmers, of course, run a business like a lot of us do, where they have to increase their farm production to really stay competitive in what is a difficult environment for farmers in a lot of cases. Regulation is changing faster in some locations or some areas of the world than it is in others. And, I think Fred talked about the availability of water. There's a lot of farmers we talk to today who say, I've got all the water in the world. Why do I need to be more efficient with my water? And in actual fact, that will change in the future as they are being carefully monitored with how much water use they have. And in the future, they may not have quite that same amount of water available to them. Water quality is also one of our drivers for putting technology into this space. We talked about some of the nitrates that are making their way out into the water, water courses in rivers and so forth. And there are technological ways that we can eliminate or at least minimize some of those nitrates that are making their way out into the water systems. Also, I think what was discussed earlier was climate change, and we are seeing a lot of more extreme patterns in the weather. We're seeing a lot more drought, and then we're seeing floods as well. So a wise man once told me that a farmer typically has one of three problems when it comes to water. He either has too much, he doesn't have enough, or it's in the wrong place. And that's really the basis of where we're looking at technology and how we can apply technology to help solve some of these key market drivers, or these key drivers for farmers to be more efficient with their water. So the three key technology areas that we look at in Trimble about how to start applying technology to address these problems is about land preparation. So we look at the topography of the field that a farmer is growing crops, and we analyze that topography to come up with a new topography where the water will be able to run off more efficiently, be able to be absorbed into the soil better, and eliminate areas of ponding or even soil erosion where a different topography could actually improve on that. So we put new design specifications around a new topography, and we go out there and we use machine control applications to cut that new surface for the field. Drainage water management. So we have turnkey solutions around designing subsurface tile applications, installing that tile, and we're working with key folks who are looking at controlled drainage applications to ensure that nitrates are held back in the field when not needed and when the crops need those nitrates. And then the third piece is precision irrigation. So this is our latest technologies that we're putting into place around looking at the field from a soil and a topography perspective, from a weather perspective, and ensuring that the farmer is much more efficient with the way the water is actually applied on the surface of the field. So starting off with our land-forming solution, Trimble, of course, has been, our roots or our core competencies started off in GPS. So we have the ability to go out there and get a highly accurate model in 3D of the surface of a farmer's field. From that, we can do some analysis where we actually look at the contours of the field. We can look at low-lying areas. We can look at steep areas of the field where water will run off too fast, take soil with it, take vital nutrients with it. And then we can put a series of constraints around what we want the field to be in terms of slopes, in terms of which way we plan on irrigating, whether it be a surface irrigation application or whether it's just simply a drainage application where we just want water to run off efficiently from the field, either in one direction or in multiple directions. And then we will do a minimal cut fill or a minimal earthworks design for that field, which stays within those constraints that whether it be a farmer or a contractor has specified. And then again, back to some of our core competencies, Trimble has been doing machine control applications for many years in terms of controlling the valves and controlling the hydraulics on a land scraper. In the construction world, we can control excavators and bulldozers, but for the most part, in this case, we're controlling a land scraper where we can tie our positioning technologies and our control technologies into the valve of a land scraper. As the operator runs through the field, the blade on the scraper will actually operate itself to ensure that the design that we came up with is applied and we can get a variable slope field without disturbing the dirt, with minimally disturbing the topsoil of the field to ensure that water will run off as efficiently as possible without ponding in the field. So the second piece of technology we have is around drainage water management. And again, this goes back to our roots of machine control and positioning applications where we can control the valve and the hydraulics on a drainage machine or a tile plow, depending on what you want to call it. But what we do is, again, we look at the topography and we determine, based upon that topography, the most ideal places to put in tile drains. Then we'll actually go out with this drainage machine and control the tile to the right depth to ensure that the drainage is applied as efficiently as possible. So drainage is, again, back to what Fred was saying with some of the concerns around nutrients making its way out into the watercourses. Drainage has certainly been controversial in that aspect of being one of the key conduits of that happening. So there's a lot of technology that's being put into place to minimize that effect. And one of the technologies is the fact that we can use GPS to do this. So rather than using the old laser technologies where a tile drain gets put in a constant slope, which means that we have a differing or a variable depth between the surface of the field and down to the drain pipe, which means that nutrients are not being evenly taken up by the crop within the field. So by using GPS, we can actually put a variable slope into that tile to ensure that the tile is at the optimal depth to ensure that the roots are taking up as many of the nutrients as possible. Another technology that is occurring in the drainage world right now is the idea of controlled drainage or drainage water management applications where they're actually putting these structures in at the end of the drain pipes to hold the water back particularly over the winter months, to ensure that nutrients are not being, the nitrates are not being removed out of or drained out of the soil when there's no crop in the field, where it doesn't make any sense. Another piece about this controlled drainage water management is in the case of droughts, we can actually hold water in the soil to ensure that the crops have enough water. So now to talk a little bit about irrigation. So this is where I want to talk a little bit about big data analytics and big data analytics and cloud-based computing. So many of us who visit farmers will know that farmers have been collecting data in their farm for many, many years. The reality is they haven't been doing a whole lot with it. They've been collecting yield maps, they've been collecting population maps, but if you walk into a farmer's office, you'll notice he'll have a pile of paper this high on his desk and a bunch of USB drives full of data that he hasn't actually interpreted into information and used that information to make real decisions, which is going to provide value to him as a grower. So around irrigation, there's really multiple different pieces of data that can contribute to how much water could be applied or needs to be applied in the field for what the crop truly needs. So one, of course, is topography. So as lower lying areas of the field, water will accumulate into those areas and there'll be more water available than the higher parts of the field where water will run off. Another piece is soil characteristics. So in the heavier soils, water will be held within that soil. There'll be more water available to the crop than lighter, sandier soils. So one piece of technology that we have in place is what we call soil information system, where we can go out and collect. Firstly, we start by collecting electromagnetic information across the entire field, and then we go out with some probes and we take some samples in specified areas within the field. It's not grid sampling. It's very specific parts of the field where we collect that data. And what we ultimately come up with is a 3D soil texture map of the field. And from that soil texture map, we can actually map plant available water within the field, which is critical to creating a prescription for variable rate irrigation. So once you combine that with yield maps and multiple other pieces like NDVI, which is effectively a measure of reflectance or crop health across the field, then we can actually come up with a prescription of what the crop needs. And then on top of that, we have some technology about rainfall. So rather than having a single rain gauge in the field, we have some technology which will give the farmer a contour map of how rain fell across that field, both in volume and by intensity. So one thing we've found is that if a farmer with a 100-acre field, he may actually have an inch to half an inch difference of rainfall from one side of the field to the other. And that makes a big difference in terms of how much water needs to be applied on that field. And we now, of course, have the technology to be able to vary the rate of the irrigation application. So the solution that we've put in place at Trimble is what we call the Irrigate IQ solution. And we've really been focusing specifically for a start on center pivot irrigation. Center pivots are today probably one of the most efficient ways of irrigating a farmer's field. But they've really been designed for applying an equal amount of volume of water across the entire field. So what we've done is put technology on that pivot which allows us to control each nozzle independently and ultimately allows us to apply a specific application depth by a defined management zone within the field based upon what the crop actually needs in the field. So every farmer knows that if they don't get enough water to their crop, it has a detrimental effect on yield. One thing that has failed to be recognised is that by applying too much water, it also has a detrimental effect on yield. So there's multiple reasons for that. One is that if you saturate the soil, there's not enough oxygen available to the roots of the crop. Another piece is that water is also a conduit for nutrients to get to the roots. So if you apply too much water, it's basically taking the nutrients below the root zone, and we end up with not enough nutrients getting to the crop, and we end up with the groundwater becoming polluted with nutrients. So another part of this solution is we have a remote monitoring and control portion of that. So a farmer might have 20, 30, even 100 centre pivots on his field, and he basically has to send somebody to drive around all those pivots every single day to check the pivot and make sure it's still running. So now he can basically take out his smartphone and check that every pivot is running. He can also turn them off in the case of a rain event. He can start them again, all from his smartphone application. We also, as we're doing all this, we're also collecting data around irrigation application. So we have proof of application for regulatory purposes of water and, of course, fertigation and effluent applications. So a little more detail on what this solution looks like. I won't go into too much detail, but we basically have some electronics on a centre pivot system that is connected remotely to, It's connected remotely to the internet. We have a cable that runs down the entire length of the pivot that has an electronic node which is connected to every single valve that we place between the pivot and the sprinkler. We also have a GPS node, of course, at the end of the pivot, so we know the exact location of the pivot at any given time. It's connected to the internet over a cloud-based application that we call Connected Farm, where all of those data pieces I talked about earlier are collected and where they are stored, and we can use that to make more informed decisions about how to apply water within specific management zones in the field. So ultimately we have a system which can be controlled in real time, where we can control application depths across specific zones within a field based upon what the crop specifically needs, providing a couple of key benefits. One is we're restricting the amount of water that is actually being used by the pivot. We're eliminating pumping costs, fuel costs, electricity costs to run that pivot. And in turn, we're also increasing crop production for the grower because he's applying the right amount of water that is required by the crop and not overwatering or underwatering the crop. So one thing we're finding is that there's the value add to the grower or the farmer is different based upon the application. Dairy is really the area where VRI or variable rate irrigation was developed. The product came out of New Zealand, where centre pivots are used increasingly for dairy applications. These guys in New Zealand are using it to not only put water through the pivot, but they're also using the pivots as an effective way to get rid of the effluent or empty their lagoons from the dairy sheds. So one thing the biggest value adds, I guess, for these guys is that they have a lot of these tracks or lanes that go through the field. If you put effluent or too much water down on those tracks or lanes, the cows walk through those lanes, they end up with hoof rot or foot rot. So we can eliminate that or minimise that by not putting effluent or water down within those areas. In New Zealand specifically, from an environmental compliance standpoint, they're very, very strict. If an inspector walks onto a dairy farm in New Zealand and sees effluent ponded in the field, it's an instant $30,000 fine, no question asked for that farmer. So by being able to show where the waters or where the effluent has been applied, and to be able to ensure that only the minimal amount of effluent is applied to ensure that this ponding doesn't happen, it's a huge benefit for a dairy farmer in New Zealand to ensure that he's not going to be hit with those fines from the environmental compliance people. And of course, on top of that, pasture uniformity and yield improvement is a big deal for these growers in New Zealand. They're finding that by simply varying the rate based upon the topography or the soil types within the field of that effluent or water application, they're actually getting pasture uniformity and yield improvements on their farms, which of course increases milk production for these dairy farmers. So this slide here I actually borrowed off a group out in New Zealand called Nightaku Farming, which is actually Nightaku is actually a native tribe in New Zealand. They have a lot of land ownership in New Zealand, which they've converted into dairy farming operations. It's actually a fairly close parallel to what's happening in many other countries, including the US. If you look down at what Navajo Nation and Napi are doing down in New Mexico and Colorado, it's fairly similar. But anyway, these guys they're one of the biggest dairy farming operations in New Zealand. Now they have 3,000 head of cattle, and they have plans to increase it to 70,000 over the next few years. So Nightaku built this slide. I've copied it word for word. And again, it's a reflection of what they're one of our bigger customers of our Irrigate IQ system, and it's a reflection of the benefits that they're seeing by utilising this types of technology on dairy farms. So they're ultimately using less water, which is a fairly big deal in New Zealand, where they're actually having to pay for the water. There's less pumping costs. When you're applying less water through a centre pivot, you're not having to spend as much money on diesel fuel to pump the water out of the ground. They're also seeing a greater crop growth, as I just talked about, by varying the rate across the field based upon what the soils are telling it. Then we can actually increase pasture production. They're seeing less nitrate and phosphate leaching. By applying the right amount of water and keeping the moisture at the right rates, they're actually reducing the leaching into the groundwater systems in New Zealand. They're also able to target their application of nutrients. So the nutrients through a centre pivot in New Zealand are specifically effluent, as I was saying, out of the lagoons. So they're actually targeting that application based upon the pasture requirements. They're also these big centre pivot circles in New Zealand. The pivots are usually half a mile wide, so they're a fairly big field, and they actually split it into multiple what they call paddocks. So if there's stock in the field, they actually eliminate the effluent application within that field where there's stock. So as they're rotating the stock through these different paddocks, they're actually being smarter with the way they're applying water and effluent within those fields. Also the ability to alarm or warn the user when a pivot goes down for any reason, just by sending a notification to their smartphone that something's wrong is proving to be a big benefit for these farmers. And of course the regulatory reporting, the ability to minimise the amount of effluent applied, ensure that ponding doesn't occur, and being able to show reports of how that effluent was applied if needed from a regulatory standpoint. So another place where we're seeing a lot of value by using precision irrigation is in grains, which is possibly more in you guys' field when you're talking about animal agriculture, as grains are clearly an important part of animal agriculture in the US. But just by optimising the water application based upon the underlying soil conditions and the topography, we're actually seeing yield increases, in some cases to 15 to 20%, just by not overwatering the field or not underwatering the field based upon what the crop truly needs. We're also decreasing groundwater leaching in these applications around grain. So potatoes, maybe not so relevant to you guys in animal agriculture, but we are seeing a different value add for farmers who are growing potatoes. Ultimately, what's important in potatoes is that the uniformity of the potato from a moisture perspective is really important, because potatoes are stored. If you have too much moisture in the potato, you end up with rot in the potato in the storage facility. So by effectively decreasing the amount of water that's applied in the field in the lower lying areas and increasing in the higher areas, we're actually getting a much more uniform potato. We've had instances where using variable rate irrigation on a potato field in Canada, where in prior years they haven't been able to harvest the whole field because potato rot is occurring in the field. By using VRI and eliminating those areas from irrigation, they're actually finding they can harvest the entire field, which is proving that these farmers are actually seeing payback in this type of technology within a single season, which is a fairly big deal for these guys. Cotton, another area which you guys probably aren't as interested in. However, I think there's some interest here in terms of being able to utilise water where it's most effective. There's some cotton growers in Texas who have been using our system, who they don't necessarily have regulations around how much water they use, but they physically can only take so much water out of the ground in a single season. So what these guys have done is they've taken yield maps from the last 3 seasons and found out the real low producing areas of the field, and they're not applying water to those low producing areas. They've basically decided, I want to take that water that I would have used in those low producing areas, increase the water application in the high producing areas, and they're actually finding that they're more profitable by doing that. They're actually getting more cotton or net higher cotton yields out of that field by doing exactly that. So back to my first slide again. Basically, by applying technology, I don't believe there's a silver bullet for solving all of these issues, and I know that Fred has got some great ideas around practices and rotating crops and using cover crops and that type of stuff, but technology also could be a key player in this field. Food security, just by using less inputs, and water is becoming one of those key inputs. Water could become the single most important or single most expensive input for a farmer in the near future. By decreasing the inputs and growing more food has to be a contributor to the food security problem in the future. And by doing that, of course, we're increasing the farm production. So land and production for agriculture is decreasing by trend, and we expect it to continue doing so. So we have to be more effective with how we grow our crops. Regulation is going to continue to occur, and we have technologies in place that are effectively showing the regulatory authorities how much water was applied in exactly in the right place. We have all the reporting mechanisms to be able to do that. Water quality is very important from a stewardship perspective, and I believe that a lot of the technologies that are being put in place means that we're minimising leaching into the groundwater by applying exactly the right amount of water that the crop truly needs. And of course, global weather patterns. We've seen droughts, we've seen floods, and having the technology in place that allows the grower to have the water that they need by being much more efficient with their application is extremely important.